guys ready? Ready for like the best team ever? So thank you all for coming. My name is Dr. Martin. This is my first semester teaching prelim. So if the team screws up, it's totally my fault. It's definitely not their fault. So we have Team CLEO here, and they are going to talk to you today about their preliminary design that they've been working on all semester. So I will let you take it away.
Thank you, Dr. Martin. So as Dr. Martin says, we're Team CLEO, and that stands for Clean Low Earth Orbit. I'm Christina Clausen, and here with me we have Spike Martin, Tim Zoller, Rachel Chrisman, Larson LeDuc, and then on this side we have Parker Heiberg, Sam Janoff, and Jonathan String. So we're going to be talking about our targeting, orienting, and actuation device, otherwise known as TOAD. So this is... Oh, there it is. So you can see our overall system on the test bed here. So we're going to go into requirements, some objectives, and the purpose of our system. So it consists of 4 distinct subsystems. They include our structural subsystem, our attitude determination and control, or ADC, our command and data handling, CDH, and our electrical power supply, EPS. Orbital debris is a significant issue when planning a mission and constructing a launch profile. So Team CLEO decided to kind of tackle this problem, but we narrowed our scope to the attitude determination control part of this issue. So our primary objectives for our TOAD is it has to be able to determine its orientation. So that's why we have the IMU there. It has to be able to move in 3 degrees of freedom in roll, pitch, and yaw. And then it has to be able to stabilize within our allotted time frame. So the concept of operations is a 7-step process. So it starts up and it initializes processes, and it will stabilize the system on the test bed. Then it will determine its orientation from the IMU. Then it will read the next target orientation. And from those 2 orientations, it will process the amount of torque needed to actuate the system to the new target. And they'll do that through the control law. Then it will actuate based on the control. So it's actuating a little bit. So then the step 6, it will read the new sensor data from the IMU to make sure that it has made it to its desired orientation. And once it is determined that it's made its desired orientation, it will go back to step 1 and stabilize the system and wait for the new orientation. So our design was inspired by Cassini, the Hubble Space Telescope, and the ERAU spacecraft. So Cassini has 4 reaction wheels, and that's what we wanted because of the redundancy that 4 reaction wheels has. Their configuration had 3 reaction wheels orthogonal from another, with the 4th as a spare. So that was kind of an idea that we looked at, and then Hubble Space Telescope also had 4, but they had it in, they were all angled, so if you lose one, you could still have the 3 degree of freedom rotation. But they had it on like separate sides of the spacecraft, so we wanted more compact since our system's going to be fairly small. So we looked at EOB, and this is the configuration that we actually modeled ours off of. We'll get into like the angles and stuff a little bit later, but it was compact, and so that's exactly what we were looking for. And I'll pass it off to Spike for system description.
Thank you very much. So as you can see, this is our current configuration. It's broken up into 2 modules. The module on the left here is the actuation module, which is contained within Lexan and ABS plastic. And the module on the right is our electronics and controls components. You're able to complete all of our critical system level requirements during our preliminary design. We shall be using the reference frame shown on the left, and both of our modules will fit within the 0.6 by 0.6 by 0.5 volume. In addition, it's very important that we shall have our center of mass within the geometric center of our triaxial test bed, which you can see right over here. We shall also be able to have a test run of at least 20 minutes from full charge. Moving forward, the reaction wheels on board shall be able to provide enough torque to rotate the entire system. And adding on to that, they shall be able to orient the entire system within 60 seconds. Also, we shall be able to determine our orientation and actuate through control law, which is done with the IMU, which is onboard module 2, with its gyroscopes and accelerometers, which goes to our field programmable gate array, FPGA, which has our control law programmed into it, and then goes to our speed controllers, which goes to our motors, which of course will actuate. We also have an optical sensor on the top of module 2 which shall assist us in tracking our target. Finally, we'll be using serial peripheral interfaces for both of our sensor packages, both the IMU sensor package and the optical sensor package, to communicate to our FPGA. And we shall be communicating from the FPGA to the speed controllers using pulse width modulation signals, which again, as I mentioned earlier, will be going to our motors to communicate, to actuate. I'll now be passing it off to Parker to talk about the structural subsystem.
Thank you, Spike. I'm now going to go through some objectives we met, some requirements that we fulfilled, and our preliminary design. So first of all, we have about the center of the ball, as you can see there, we have a roll angle of 360 degrees, a pitch angle cumulative to 51 degrees, and a yaw angle of 360 degrees. We have the module 1, which aids the ADC group with a fixture to hold the reaction wheels. And module 2 is in charge of containing the electronic components and the EPS as well. We fulfilled our requirement of being within our weight restriction of 7 kilograms. As you can see, our structure is comprised of ABS plastic, polycarbonate sheets, nylon standoffs, and a 1 kilogram countermass. The electric components had a requirement to be insulated. As you can see on our Raspberry Pi, we have a standoff, nylon standoff, and the electronic speed controllers and voltage regulator, as well as the batteries, are held in place by Velcro and Velcro straps. The preliminary design of this was to basically orient this device, as shown before me. We were able to limit the amount of weight on our project by using this hollow airball bearing, so we could wire between it without using additional countermass. As you can see above me, we have holes in each corner of our modules. This is to add counterweights after we actually put this on our test bed. So we want to keep our center of mass in the very center of the ball. And as you know, SolidWorks can only tell us so much about where our center will be. So we need to actually fix that once we go into testing. Module 1 contains the reaction wheels and allows us to have a safe environment for users so that no one's fingers can get stuck in the motors. We found that very important to limit that. Module 2 has an optical sensor that has an unrestricted viewing angle, so none of the other electric components are hindering that. The FPGA and Raspberry Pi, as you can see, have accessibility as well as the batteries for replacement or charging. Module 1 was designed to be as symmetric as possible, so the reaction wheels are placed adjacent to each other, 45 degrees or 95 apart, 90 degrees apart, sorry. And this is an inner and outer view, and this figure on the right above me displays an assembly feature. So if you didn't get that from the first year. This is the inner plate of our module 2, which holds our IMU, which is sandwiched between the inner plate and the outer plate because it is pertinent to our design, because it compiles all of our data and is very important to our simulations. So the optical sensor, as I said, is on the outer module, and the speed controller, 4 speed controllers, and the voltage regulator are underneath this outer plate. Once again, you can see more from this visualization. I'm now going to pass you off to Tim for electrical power supply.
Thank you, Parker. I'm going to go over the EPS, Electrical Power Supply Subsystem, and teach you guys why we need it for TOE. So, what is the EPS? The purpose of the EPS is to provide power to the entire system. So here is a wiring diagram. I will go into more detail about this later in subsequent slides, but this is the main overview of what the EPS does. Our first requirement for the EPS is to have a weight no less than no more than 2.5 kilograms. Currently we have 1.95 as you can see here. Most of that is the 4 luminaire batteries which we're using to power the EPS and Toad. Our next requirement was that the EPS shall output at least 10 volts to all other subsystems. As you can see on the right, there's the 10 volts. And on the left, we have the 4 luminaire batteries, which are placed in parallel, which are providing us 15 volts. The final requirement for the EPS is that it shall regulate the voltage correctly to all other subsystems and components so that they function without catastrophic failure. Again, here's that wiring diagram, which I will go into more detail. So, how did we choose any of these components? We looked at 3 things, basically: cost, compatibility, and credibility. So first, cost. The FPGA was given to us, I should say at least 20 FPGAs were given to us by Dr. A from the electrical engineering department to help us out. And the UBEC, as you can see number 11 right here, UBEC standing for Universal Battery Elimination Circuit, or voltage regulator basically, is very cheap. So those were 2 of the things that helped us choose those components. Secondly, compatibility. So the number 9 is the battery 11. They're both made by the company Luminaire and are compatible, as well as the speed controllers and the motors. Those are both made. So finally, credibility. The Raspberry Pi, that's our computer, Raspberry Pi Model 3B. This obviously, I mean, I'm sure everybody knows what a Raspberry Pi is if you're in this room. And there are millions of people worldwide that use it. So if we get stuck, we have people to back us up. Finally, this lovely wiring diagram. So we get these 15 volts from the 4 luminaire batteries, and we're sending those 15 volts to the 4 speed controllers up here. Those speed controllers will in turn power the motors, which will then actuate Toad. Here's the UBEC, or the voltage regulator that I was talking about earlier. This UBEC will take those 15 volts from here and put it, send it down to 5 for the Raspberry Pi here and the FPGA. The FPGA then has an internal regulator, which takes that 5 volts to 3.3. And now that 3.3 volts will power the IMU. Next, I'm going to pass it off to Sam for the ADC subsystem.
Thanks, Tim. The operation of our ADC system will consist of the sensors sending data to our control law in the form of quaternium, and then the control law will send an actuation torque to our actuators, and then the actuators will actuate and change our current orientation, which the sensors will sense, and so on. Our first system level requirement was that the ADC shall be less than 8 kilograms, which it is by a great margin, and weighs 2.25 kilograms total. There were several trade studies conducted for our method of actuation, the first being reaction wheels, and the second being control moment gyros, and lastly thrusters. Excuse me. We ended up going with reaction wheels because of their simplicity of implementation and due to the scope of the project. The control moment gyros were much too large for us to implement in the current time period, and there was a lot of structural implementation that would have to be done to implement thrusters because of their fuel. So we ended up going with control moment gyros, and next is how we orient our control moment gyros, our reaction wheels. We orient our reaction wheels as seen in the figure, where each reaction wheel is tilted 70 degrees from this axis here, respectively. And if you were to draw a center line from the origin to the center of the reaction wheel and project it onto the YZ plane, it would be both 45 degrees from the Z-axis and the Y-axis. And next is to talk about the preliminary design of the ADC. Rachel.
Thanks, Tim. I'm going to talk about the preliminary design for the ADC. So we chose a linear quadratic regulator, or an LQR controller, as a means of an attitude control system. First, it's going to interpret our orientation, then it is going to calculate the adjustment that is needed, and then it will apply the adjustment. And the great thing about an LQR is that it's a continuous controller. It is a closed loop system. And also, the steady state error is included in our equations of motion, so we don't have to have an integral controller to drive our steady state error to 0. So there's a few more really great reasons why we chose the LQR. One is that it's an optimal proportional derivative controller. So it's an optimal PD controller. So since it's a PD controller, it has 6 gains. There are 3 proportional gains, 1 in each direction of roll, pitch, and yaw, and there are 3 derivative gains, again, in roll, pitch, and yaw. So since we have 6 gains, it's fairly easy to tune the LQR to do what we want it to do, to be within our requirements. And since it is an optimal solution, it's an optimal PD controller, so the solution for each of those gains is always optimal. So no matter what gains you put in there, it gives you the optimal solution for those gains. So I'm going to go into this is our LQR. I'm going to go into it a little bit. This is the high level scope. So within this green box, that's going to be our controller, and that's going to be programmed on our FPGA. If you look, we're using quaternions, and that is a 4-element vector that describes our orientation. That's going to be sent into our error block right here. We're sending in our target orientation, and we're comparing that to our current orientation, and that error is sent into our controller. Our controller then does some calculations to determine the torque that the system needs. That torque goes into our calculations for our actuator block. It's going to spit out the angular acceleration needed for each reaction wheel. That's why it's 4 by 1. There are 4 reaction wheels. We need 4 different numbers. And it also spits out the torque that we're at right now. All of that is going to go into our sensors and actuators section. And so here it comes in our actual torque, right here. And then it's in our vehicle dynamics block. So we're going to get our new quaternion, and that will be sent out, and so will our angular velocity. All of that, then you can see both of those, come out and go back into our controller block, and that's how it's continuous. It's going to go over and over and over again. And I'm going to send you to John for our simulation and analysis.
Thank you, Rachel. There are 4 requirements that can be used to describe the system that the LQR controller must control. That is time, error, velocity, and stability. As you can see here, the system is rotating from an initial orientation to a final orientation. As it rotates, it ensures that it will not pass a maximum of 15 degrees per second and then reaches stability at the final orientation. It must do this in 60 seconds, and qualitatively, this animation shows that it meets those requirements. This graph here, represented by the black line, is the angular position in yaw for that previous simulation. These red lines represent the plus or minus 1 degree of error that is allowed for the LQR controller at stability conditions. And it must do this in 60 seconds. And as we see in this graph, it reaches that in 60 seconds. Further analyzing that graph, we find that the red line indicates the angular velocity of the yaw. And as we see, that quantitatively, the yaw does not exceed the maximum velocity of 15 degrees per second. Looking at various different changes in orientation, we can see that those requirements are still met, proving that our system can match a variety of systems, or variety of orientations. For this one, we have a simulated maximal rotation or large angle rotation, and we show that we still meet our stability requirements, our error requirements, our time requirements, and our velocity requirements. The same thing can be shown in this large negative angle rotation and for the small angle rotation, which the graph surface was not different. On to Larson. Let's talk about the CDH subsystem.
Thank you, John. So the purpose of the CDH subsystem is to take the data from the sensors. So it will take the IMU's data in the form of our current quaternion, It will supply that to the control law. The VDPU, or Visual Data Processing Unit, which is made up of the optical sensor and the Raspberry Pi, will supply an attitude correction to the control law. And then inside the control law, the control core, or the FPGA, will be supplying, or taking those in using the LQR controller, and be supplying an angular acceleration to the actuators. And the actuators, the speed controller will take that angular acceleration and convert it into a voltage for the motors to reorient the system, and then the system will have a new current orientation, which is then once again resensed by the sensors. So Toad uses two different forms of communication between all the different hardware components. The IMU communicates to the field programmable gate array, or FPGA, using SPI. The Visual Data Processing Unit will communicate to the field programmable gate array using SPI, and then the FPGA will communicate over to the speed controllers using post-width modulation, or PWM. Now, this is a detailed view of what is occurring inside the FPGA. Inside the FPGA, we have two SPI nodes that are in parallel connected to the RAM of the system. From there, we can access the RAM's data using a user interface, or we can input new target orientations, or we can access it using the control core, which will then supply back to the RAM to the PWM nodes, which are in parallel, to go out to the speed controllers, thus reorienting the system. And now I'll hand it back to Christina for our summary.
Thank you, Larson. So, just a couple lessons learned. Throughout the semester through the preliminary design process. As you can see, this is not what our design looks like anymore. This is what it was for the majority of the semester, until we realized it was an inverted pendulum problem and not a spacecraft attitude disturбation problem. So a little last-minute design change. We learned from that. We learned to go to faculty members a little bit earlier on and get some advice, because they're willing to help, and we like their help. Another thing we learned is throughout this preliminary design process, all the documents that we've created and finished, we had to complete on time to keep the design process moving and keep it progressing in a reasonable rate, so we weren't falling behind or anything like that. Because if we did, this design would have changed a little bit more. We would have been a little bit farther behind, and so we probably wouldn't have been able to make a new design as quickly as we did. So in conclusion, our preliminary design has satisfied all the requirements that we have thus far through our simulations. Moving forward in the detail semester, we plan on creating this design and testing it to verify that we actually do meet the requirements we said that we would. So that's the plan for the future. We want to acknowledge Dr. Khan for his generous donation and support for our project, and without that we wouldn't have the components that we are planning to get for the precision needed for our project. Are there any questions?
I love the visual of the weight, by the way, and I appreciate your sense of humor. My question is, it looks like you easily met all the specifications of the requirement. Which specification was most constraining, and you can include cost?
Could you define including cost?
So you have engineering specifications that you easily met.
Right.
So which requirement was most constraining in your design? And you can include the fact that cost was a constraint as well. So which one would you select as the most constraining requirement?
During our trade studies, all of the components, cost was a design metric, or not design metric rather, was something that we took into consideration. For a significant amount of time, our batteries, we weren't sure if they had enough volts to be able to generate enough power to be able to do the full 20 minutes. However, with some adjustments to the system, we were able to overcome that issue as well. Other than that, I believe most of the components were fairly under control.
Okay, so good news, bad news. The good news was I thought the presentation was very good, confident. I loved your graphics; they were very helpful. I loved the animation because that really did help a lot. But I had one fundamental problem, and it may just be my brain because my brain is jet lagged by 7 hours at the moment, so I'm ready to sleep. But I have no idea what this is for. So I've got a very good description of how it works, how you put it together in design, but I couldn't see what the relationship was between what you described and the title of the program, or indeed debris. Now, it may be that it's obvious and I just completely missed it, but could you just explain again? Because, by the way, on the first slide, you need to say what CLEO stands for. You told us verbally, but you need to say always on the first slide what the key acronym is. And then what is the relationship between orbital debris, which I agree is a huge problem, and this? I was expecting something that was either going to avoid debris or collect debris or do something with it.
Yeah, so that was the main problem that we wanted to tackle, but since this is only a year project, we wanted to narrow our scope and we wanted to focus on the attitude determination problem of something that could track orbital debris. So using a database that Lockheed Martin already has a database of some orbital debris that's in low Earth orbit, and so using that database, that would be our our target orientations that are provided by the FPGA, so they'd already be loaded in. And so what we're focusing on is orienting towards the debris. So we're not focusing on the collection method, we're just focusing on the attitude determination to track the debris, in essence.
This is ground-based or space-based?
Space-based.
We're
Oh,
testing
testing
on
is
that.
ground-based.
Right. Okay. So you have an imaging system or radar system or something?
Well, we
That's
have.
somebody else's part of the program that fits in with it? How are you tracking?
Okay, so
So we already have the database from Space Fence from Lockheed Martin, well, in theory, of course. And so we were saying if we know the coordinates, then we should be able to orient towards the coordinates, given that we can determine our own attitude. However, to assist in the tracking, we also have an optical sensor on board, which we'll hopefully, through our secondary objective, be able to use to more effectively track our target, which would in theory be the pieces of debris.
Okay, did I miss it? Did you say on here you have an optical system somewhere?
I did mention it, but I may have mentioned it too quickly.
All right, thank you.
Well, I'd like to agree with comments previously made, so I'll try not to repeat too much. But overall, yes, the graphics were extremely helpful, but I'm kind of in the same boat. I'm sitting here like, what is this? But you kind of already answered that, so we'll go to a few other things. If you could go to slide 6, please. The one that's labeled 6. It's really like one.
I didn't press it.
I think Google Slides does not have the 6 enter macro, unfortunately. Yeah, for some purposes.
So, this is more just a question of grades. ERAU-B, I'm unfamiliar with it. What is that? System Pro? I just don't know what it is.
High energy astronomical observatory.
Okay. Okay. Just didn't know what it was, so I was curious. Okay, if you go to slide 11.
11?
Yes, please. I know this is kind of a pain, but the one labeled 11. Yes, that one. Okay, so this is the point where I started to asking the same questions of what are your requirements, how you know they're satisfied, simply because they weren't presented. So that would be something I would advise you guys to do in the next presentation is show your requirements and then show how they've been resolved numerically or via some other metric. Sometimes you're just checking a box and saying, yes, it can do it. Like, yes, it weighs less than this, just for example. Slide 24, please. I'm kind of picking on some of the technical details because Kyle was mostly taken care of. So, EPS shall provide 15 volts more than the required 10 volts. Can you use those 15 volts?
Yes,
John?
we can.
Okay.
Yes, we can use those 15 volts. The speed controllers are what's the word, spec'd out to 15 volts. They support it up to 40, I believe.
Okay.
And so 15 volts allows us a higher torque, so we can rotate faster.
Okay. Okay. So you don't need that then.
We don't
but
need
you can use it.
Yes.
Okay. I'm asking because I thought it was unusual that you chose voltage as your metric as opposed to like amp hours or power. It didn't quite make sense.
Another thing that we could say for this is that battery voltage tends to drop, and having a higher voltage allows a larger margin.
Yes. Let's see. So slide 32, please. One more.
All right.
Or actually, that might have been it. No, this is it. So the only thing I would like to see on this slide is if you could have shown your criteria matrix for how you arrived at the decision. I'm not necessarily arguing with the choice, just more of a showing how you arrived at and showing the metrics you used. So for example, if you were to say simplicity, okay, simplicity in what way? Parts, cost, like what do you mean by those things? It just gives you traceability as you go through, and it makes it easier to look back on things and explain. Here's why we did this. Because 5 years down the road, when half the team is gone and the other half that is still there are all management positions, they'll look back and be like, I have no idea why we did that. Slide 37, just a small comment on graphics. Please work on your colors. I cannot see the green at all. I know you guys did a good job explaining it. I was just looking at it like, this looks very familiar because it looks like what I did some 3 years ago, but I can't see it. Slide 39, please. All right. So I can't remember who the presenter was at this point, but you stated in 60 seconds. Why was 60 seconds used as the timeline?
That was our requirement to stay within, under a minute.
Okay.
Our orientation.
Okay. So that just goes back to ensuring the requirements. Because I was just sitting here thinking, why 60? Why not 2 minutes? Not 5? Okay, fair enough. All right, overall, like I said, the graphics really help explain things. Appreciate that. Just show a lot of the thought that goes into it, like the requirements, and that'll clear up a lot of these questions. Just make it, I guess, more streamlined. And one quick thing too as well. And please show a quick summary of how your requirements have been satisfied. I only say that because that helps me as the judge, presenter, panelist, whatever I am that day, remember where I'm at. Because when you're going through a ton of subsystems, it can get very easy to get lost. And keep in mind that this PDR is relatively small compared to the ones you'll see in industry. In industry, they get much bigger. So that's very helpful to have those summaries and just say, okay, here's where we're at.
Thank you.
Good job, you guys.
Yeah, color graphics were really good. They really help get your point across, but I guess kind of summing up what everyone else said, you could use like a little bit more text. Since we're sitting here trying to listen also, but also write down notes, it's hard to catch up if we get lost and we can't read what's going on. But I thought it was really cool that you guys picked like a space project. I feel like a lot of them, they get kind of grounded and it's like, you're an Astro Trek, but we're not really doing something spacey. So you guys you did a really good job of finding a terrestrial way to, do a space project.
Thanks.
I think everyone else kind of covered what I wanted to say. So,
Are there any other questions from the rest of the audience? Because we still have some time left.
Who made the logo?
Nice job. Thanks.
Do you want to ask? Oh, yeah, go ahead. All right, good.
Okay, so I had. I had somewhat the same difficulty you had discerning. Well, I sort of had, in the context of the introduction, what your purpose was here to basically define something, orient toward it so you could track it. Now you're using, it sounds like you're using a two-step method involving this database to get an approximate location, and then you zeroed in using there's going to be an error in the database. So your optical acquisition system is going to have range to be able to acquire the object once you've gotten across the location. So do you have any idea how accurate that system has to be in order to acquire the object and obtain the final orientation?
Unfortunately, we don't know how accurate the database is yet, but we can adjust the cameras so that it can operate within a certain range, or we can add more sensors to the device.
What is the field of view?
It's about
That's probably enough.
it's pretty wide.
If it was that, then I'd be worried, but if it's that.
The optical sensor program and all of its
Okay, so
specifications
you
have
think
been
you have a
designed.
wider net field of view than the other?
Yes, sir.
That was fine. Thanks.
Yeah, can ask them.
Yes, we have time.
Okay, this one's a little easier. So, as a team, what did you guys find were the challenges you ran into?
The design change a little last minute. That was probably the biggest one.
When was that change?
It was a week ago.
I can imagine.
To clarify, we were doing the control law correct, we just didn't have the correct structure.
Fair enough. So, not quite what I meant, but more of a, from working on a team. So, most of what I do is more working with government and things like that. You're working on big teams that are far away from each other, and a lot of times they don't like to talk to each other. Did you guys run into any of that?
Not really. For the most part, our team has been pretty coherent. We did have 2 new members added towards the end of our semester, so integrating with that, 2 new members, it wasn't too difficult because our class size at the school is pretty small. We already kind of knew each other, so we didn't really run into too many of those problems.
Okay, fair enough. Yeah, I was just curious because sometimes that can be most of the projects I've seen that's kind of your make or break point is people get along. In industry, fortunately, what you can do is you can fire people who don't get along, but in teams like this, not so much. So it was something I was curious if you guys would run into any of that because team dynamics oftentimes will determine your success. Yeah. So.
Thank you. Any? Yeah.
Yeah, one of the things you've got in the back of your mind, I'm sure, is that you want this to be a success by the time you finish it. But things with luck will go wrong, so that's how you learn. But what you didn't present at all was a risk analysis of anything. So what do you think, I mean, thinking about it in real time now, what are the biggest risks to the success of this project? Both technical and human.
I'd say having like our countermass not properly in the center, and then being off kilter, and then not being able to correctly adjust for that. As you can see, our inverted pendulum, that was a problem. Another issue could be whether or not we're moving at the same speed as our target, if we can calculate that. That's it. Does anyone else have something to add?
And then another problem that we've trying to get ahead of for detailed semester is the reaction wheels we're going to have to manufacture on campus. So the precision needed for that is pretty high. So.
Have you done any sort of analysis of how accurate you need them? Well, there's 2 things. One is defining how accurate they need to be, and then the second is having them built or having them procured, and then measuring the accuracy.
We haven't talked about, we haven't determined how accurate they need to be, but we have talked to the machinists on campus, and I don't recall the exact number, but it's going to be very precise.
Yeah, I don't recall the exact number, but the campus just has a new CNC machine, and 2 of our machinists are very skilled in using it, and so we've got confidence from people saying that we can do this on campus, and then they can measure the precision of it for us.
Okay, so that's why it's really important to get the quantum. I mean, CNC machines are incredible, and they'll be capable of manufacturing things far greater accuracy than you need. You've got to specify them right. So one of the things that I really suggest you do on the project is to play devil's advocate, think of what can go wrong, do a risk analysis, then come up with some mitigation. because you've got the skills, clearly, from what you've presented so far. You've got the skills to do it.
Do you have the air bearing cable that exists?
We have the ball portion of it right here, and then the actual test pedestal weighs about 500 pounds, some exorbitant amount of weight. So we don't plan on moving it over here for the presentation. Yeah. It is on campus. We do have the capabilities.
Any other questions? If not, we've got, I forced them to go short, so that's why. So we've got 30 minutes, the next team starts at 11:45, right? I'm right about the schedule. So, student break,